Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Faisal Kabir Manizam, and today we will present on our finding on project mathematical model and simulation of a DC motor. So, this is my teammate, Ratimala Chelvi, Maakif, and Muhammad Isan. Okay, so the first part is motor speed versus load to characteristic of a DC series motor. So, as you can see, this is how we build the circuit, and the stock sensor and speed sensor must be connected to the motor and between motor and motor load to get the result. So, and this is the and table 1 show the characteristic table for motor speed versus the motor. And this graph show the motor speed versus load characteristic. So as you can see here, the higher the load, sorry, the higher the load, the lower the speed, the higher the higher the motor speed will become. And this is two sample simulation result. The first one is motor speed, motor torque, and armature current graph for motor load for 10 Newton meter. And the next one is for 500. You can see here. So you can see the difference here. And this is of the result. This is the motor speed graph, motor torque graph, and armature current graph.
Hi, I'm Ratimala Chelvi Saravan and my matrix card number is B0822101159. Today I'm going to explain the calculation related to this project. So as we see, we already have got our measure result. So what are they asked in the project? The question is, calculate two sample of motor torque, motor speed and armature current from the simulation parameter. As we see, we took a two sample which is 10, the load torque 10 nm and 200 nm. So the maximum, the TL equals to TL, which is load torque is equals to the maximum torque. As we see, I calculated the constant torque. When we calculate the formula for the constant torque is maximum torque divided by armature current square. So when we divide, we will get 1.39. So for both torque load, we got the same constant, which is 1.39. And then we use the voltage terminal formula to find the voltage terminal, what is the difference between the voltage terminal. So for the 10 nm load torque, the voltage terminal is 286.6 voltage, and then for the 200 nm load torque, 240.09 voltage. So when the load torque is increases, the voltage terminal is decreases when we compare to this calculation.
My name is Muhammad Akif bin Muhammad Ismadi. Today I would like to present our project mathematical model and simulation of a DC motor. Okay, for my part, I will present the part B, speed control of a DC series motor. For this project, we measure the motor speed when the load torque was 30 Nm. Initially, the motor ran at a speed of 408 rpm with an emitter resistance of 2 ohms. We increased the emitter resistance. The new motor speed was 300 to 6.4 rpm, and the new emitter resistance value was calculated as 80.832 ohms. Okay, for the simulation result, for the circuit before, the DC voltage is 300 voltage supply power to the circuit. The emitter show a current of 4.64137 ampere. The motor is connected in series with a emitter resistance and field winding. The load torque implied is 30 Nm and the motor speed is 408.93 rpm. At this stage, the resistance is still at 2 ohm and the motor operates at its initial speed. for the after circuit, after increase the ammeter resistance to 80 80.832 ohm, we observe change in the circuit. The current increased to 7.34916 ampere, indicating highest resistance. The motor speed decreased to 300 to 6.46 rpm, aligned with our target reducing of 20%. The implied voltage remained at 300 voltage, but due to the increased resistance, the voltage drop across the ammeter increased, reducing the effective voltage across the motor. This confirmed that increase the ammeter resistance effectively reducing the speed of the DC series motor while maintaining the same torque load.
Number 7, they asked to summarize your findings and show the simulation result compared with your calculation. So the initial, as we see the measured result, the initial speed of motor speed is 408 rpm. So what they request is we have to reduce the 20% of motor speed and then find out the armature resistance. Okay, when using the calculation, the reduced motor speed is 326.4 rpm. So when we measure, we also get same as the measured value, as the calculated value. So the first armature resistance before reduce the speed, motor speed is 2 ohm. After reduce the speed, we measured the ohm is 18.83. So when the motor speed reduced, the armature resistance is increasing.
Okay, next I will present the part set ammeter resistance as before. Measure motor speed when torque load is 40 Nm and 10% of a motor speed by vary the terminal voltage. Okay, for this part, we set the ammeter resistance as before and measure the motor speed when the load torque was 40 Nm. Initially, the motor operates at a speed of 349 rpm with a terminal voltage of 300 voltage. To reduce the motor speed by 10%, we decrease the terminal voltage. The new speed was 314.1 rpm and the adjust terminal voltage was 272.3 voltage. Next, I will show the simulation result for circuit before. Here we see the original circuit before lowering the terminal voltage. The power supply provide 300 voltage to the motor. The ammeter show a current of 5.3594 ampere. The motor is connected in series with the ammeter. The motor is connected in series with here the field winding. The implied load torque is 40 Nm and the motor operates at 300 for 9.55 rpm. At this stage, the motor is running at its full supply voltage. Next, I will show the result simulation for after circuit. After reducing the terminal voltage to 207.2.3 voltage, we observe the following change. The current remains at 5.3594 amperes, indicating that torque remain unchanged. Then the motor speed decreased to 300 for 14.1 rpm, meeting our target of a 10% reduction. The voltage drop across the motor decrease, result in a lower speed. This confirmed that reducing the supply voltage effectively decrease the motor speed while maintaining constant torque. That's all from me. Thank you.
For number 8, is same as the before, but here they reduce the motor speed as 10%, and also they compare the voltage terminal. As we see, the initial speed when we measured is 349 RPM. When we calculated uh, the 10% reduced speed, we got 314.1 RPM, same as the calculated value is equal to the measured value. So here we use the formula to find the armature current, which is IA equals to square root of TL over RA plus RF. So here we find the voltage terminal first for the armature current, which is EAO, which is we got 286.0 voltage. And then we calculate using the EAO to get EA1, which is 257.4 voltage. Overall, the voltage terminal, the after voltage, that is a two voltage terminal before and after. Before voltage terminal is 300, after the voltage terminal, which is we calculated is 272.3. But in calculation, uh, we got 271.4, which is very close to our measured value. So this is the calculation for this part.
Hi, my name is Muhammad Isan Rizki, and I am going to continue our presentation regarding discussion and conclusion about our project. Simulation and analysis of the DC series motor in this study provides a comprehensive understanding of its speed torque characteristics and speed control techniques. Regarding the speed torque relationship, simulation confirms the inverse relationship between speed and torque, where increased load torque results in reduced motor speed and higher armature current. With the speed control techniques, effective speed control was achieved by reducing speed by 20% through armature resistance adjustment and 10% through terminal voltage modification, demonstrating predictable outcomes. And regarding the simulation effectiveness, the use of PSIM software successfully modeled DC motor behavior and validated fundamental principles of electrical drives under varying load conditions. In conclusion, the simulation and analysis of the DC series motor using PSIM software effectively demonstrated the motor's speed torque characteristics and speed control techniques. Regarding the speed torque characteristics, the simulation confirmed that increased load torque decreases motor speed while increasing armature current and motor torque. Regarding the effective speed control, speed regulation was successfully achieved through armature resistance and terminal voltage adjustments, aligning with theoretical expectations. And finally, regarding modeling accuracy and practical value, the PSIM simulation accurately modeled motor behavior, highlighting the importance of parameter adjustments for practical applications in electrical drives and control systems. That's all from me today. Thank you for your attention. My name is Muhammad Isan Rizki, and I'll be signing out. Thank you.